So remember, we have something called a sequence. And a sequence is an infinite list of numbers, often written with like a sub k. And then we can take that and turn it into a series, where a series is where you add up all the a sub k's. You basically take all the numbers. So an example might be 1, 1/2, 1/4, 1/8. That would be an example of a sequence. And then the example, if we turn that into a series, would be 1 plus 1/2, etc. And so in each of these examples I've given, these are an infinite sequence and an infinite series. And you may recall by looking at these that these are a geometric sequence and therefore a geometric series. And the reason is that in each case, we're multiplying the previous number by 1/2 to get the next number. And so this gives us an ability to express these with a formula. And in the case of the infinite series that we get, we could even get this total, because the total was where you take the first term and you divide that by 1 minus r, which is the number you're multiplying by each time. And if we did that in this case, we would get 2. And so when you have an infinite series, that the total that you get actually settles on a value, then we say that that series converges. So in this case, we would say this is an infinite geometric series that converges to 2. So we had all kinds of different kinds of series, and we had all sorts of different tests to see if they converge or if they diverge. And let's do maybe an example of one of those kinds of problems. Okay, so consider as an example, and this is on page 659. So this is the review exercises for all of chapter 8, and I'm going to grab maybe 18. So number 18, it says, evaluate the following infinite series or state that the series diverges. So evaluate or state that it diverges. And the series that we have to look at, number 18, is we have the series as k goes from 1 to infinity, 4 to the minus 3k. Okay, so in a lot of the problems in chapter 8, we are not tasked to either evaluate or state that it diverges. We are instead tasked to simply determine whether it converges or diverges without even figuring out whether it converges to a particular or what particular number to which it converges. So the fact that in this problem, they say that we might be evaluating this means that in most likely it has to be a certain kind of series, because the only kind of series where we actually evaluated the number when they converged, as in our previous example where we got a 2, was typically with a geometric series, because then we have a formula for what it converges to and when it converges. So that might help us recognize that, we would suspect that this is a geometric series. And again, a geometric series, you get each successive term by multiplying by the same number over and over. And we call that number R, which is the ratio of successive terms. So we would like to see if we could imagine that this can be seen that as k goes up 1 each time, that we just multiply by a different number. So I'm going to rewrite this a little bit so that we can maybe make it easier to see this. 4 to the minus 3k can be seen as 4 to the minus 3, all raised to the k power. And that means that each time that k gets bigger and bigger, you just multiply by another 4 to the minus 3. What is 4 to the minus 3? That's 1 over 4 to the third, which we can see 4 to the third power is 64. So this is 1 over 64 to the k. So we can see that this is a geometric series in which the R value is 1 over 64. And therefore, we have a geometric series R equal to 1 over 64 and a sub 1, meaning the first value when k is a 1, is 1 over 64. And therefore, the sum of the series is equal to a sub 1 in the top. That's a 64, if I can get it, divided by 1 minus the R value, which is the same as the A value, because it's a geometric series. So we could simplify this by multiplying by 64 on the top and the bottom to clear those little fractions, and I would get 1 over 64 minus 1, which is 1 over 63. So therefore, we could conclude that this can be evaluated to give you 1 over 63. Questions, comments, or discussions about this example problem from the exercise set in chapter 8? Okay, let's maybe move a little bit further down the list. In fact, as I always like, I see some problems here. And these are book problems, which allows them to be open-ended. So let's move down and take a look at, oops, I want to just keep the black color. Take a look at number 55, same page. So there's a couple parts to this. Looking at part A, it asks the question, does the sequence, and it puts the formula in the sequence notation, k over k plus 1, does the sequence converge? And it asks why or why not. So Christian suggested it diverges. And just to be clear, because the book wrote the word, but I didn't, this is a sequence, not a series. So let me put a couple of terms here. So the sequence, if k is a 1, we would have 1/2. If k is a 2, we would have 2/3. If k is a 3, we would have 3/4. And I'm just going to go ... at that point. So we have one opinion given, at least assuming I phrased the question well enough. Does this sequence converge or diverge?
I think it'll converge.
Converge, chimes in Parjit. And do you see it converging to a particular value, or do you just see converges but not sure to what value? Or do you have a further opinion, Parjeet?
I guess based off of the terms in the sequence, it seems to be headed off closer and closer to 1.
Okay. Couple opinions there. Anybody else have an opinion you want to share? Okay. So when you're looking at a sequence will converge or not based on if the limit as k goes to infinity of the terms of the sequence exists or not. So again, for a sequence, we are not adding up these values. That would be a series. We are just have a list of numbers, and a sequence will converge if the numbers showing up in the list are settling in on a value. And you can determine that by taking the limit as k goes to infinity of the formula for the terms of the sequence. So in this case, you may recall that this is a limit that we can evaluate, and maybe the easiest way to remind everybody of that is by adjusting it algebraically. If I multiply the top and the bottom by 1 over k, I'm dividing out by the biggest power of these polynomials in this rational expression. Then this simplifies to being the limit of 1 over 1 plus 1 over k. And then when you write it that way, as k goes to infinity, you can see that this little part here shrinks away to nothing. And that means that we have the limit as k goes to infinity of 1. So the conclusion for this would be that the sequence converges to 1. Questions, comments, discussions about that? So then part B, since this was part A, asks if the series converges, and if so, why or why not? So we have the exact same formula, but now we're making a series out of it because we're adding everything up, and we're asking if this converges or diverges. And of course, why or why not?
We could figure it out by taking the limit of the partial sums.
That can be an approach. So let's say you wanted to try to do it that way to think about it, even just to wrap your mind around what the question is asking about. But keep in mind, you have the right idea, and I think we discussed this a little bit before, so think about it. You have the right idea as to what's going on, but you don't normally have a formula for the result of the partial sums. And so if you don't have a formula for that, then practically it's kind of hard to take that limit. You could think about that numerically or graphically, but in terms of actually formulaically taking a limit, like what are you taking the limit of? Does that make sense, Parjeet?
Yeah. So could you instead see which way just the sequence of the partial sums are headed?
Yeah, definitely it's worth sort of looking at, especially because a lot of times people don't really understand what the idea is here. So let's sort of explore here. Explore the partial sums. So S sub 1 would be just the first term, which we already figured out when this was a sequence, which was 1 over 2, right? So then S sub 2 would be the first term plus the second term, which was 2/3, right? S sub 3 would be equal to 1/2 plus 2/3 plus 3/4. S sub 4, 1/2 plus 2/3 plus 3/4 plus 4/5. So you can add these together or try to imagine what's going on, but this is the goal. So basically then we would want to take the limit as k goes to infinity of S sub k. So that's what Parjit was saying. You're going to take the limit of the partial sums. But as I was describing, this probably isn't the best way to do this problem. This little exploration that we're doing here is a good way to understand what the problem is asking, but it's practically not very helpful for actually doing this because we don't have a formula for what that total would be out to the kth position. We did if this was a geometric series, but it's not. So if we had a geometric series, we have a formula for a finite sum or a partial sum of a geometric series. But for our other series, we don't. So we kind of like, you can imagine what's going on, but it doesn't give us a practically straightforward way to figure out whether it converges or not. Does that make sense, Parjit?
Yeah, that does.
So we do have a couple people saying divergence using the divergence test from Palm and Madison, and that's completely correct. So that's the thing. So Parjit, you're thinking about this exactly the right way and what we're trying to determine, but the thing to recognize is that the way we determine whether the limit of the partial sums exists and whether it converges to a value is with all of our various tests for convergence or divergence. And the very first one of those was the divergence test. And so Madison or Palm or anybody else want to chime in with how the divergence test would show us that this series diverges? Let me kill my phone here. So for those who are not thinking of the divergence test right out the gate, the divergence test says that for any series that's infinite, to have a chance to converge at all, the limit of the terms of the series must be 0. Therefore, if the limit of the terms of the series is not 0, the series must diverge. So I would say, since in part A, we concluded that the limit as k goes to infinity of k over k plus 1 is 1, which is not 0, then the series diverges by the divergence test. Because the divergence test says if the terms in the series don't go to 0, the series has to diverge. The only way you can have a chance to add up all these numbers and have the infinite summation settle in on a value is if the numbers you're adding as you go down in the sequence are getting smaller and smaller and going to 0. In this case, they are getting bigger and bigger and approaching a value of 1. And if I add up a bunch of 1s off to infinity, I'm not going to converge to a number. I'm going to diverge and head off to infinity.